we have here a stack of disc weights. Now this stack has a potential energy. Matter of fact, we can build the stack up the top of any one of these discs. If I lift this disc, there's a potential energy. It attains a potential energy. I lift another one, I do some work, more work than I did with the first one because I'm lifting it higher, and there's more potential energy, and here's more, and here's more. I'm progressively adding potential energy to this stack by lifting weights, doing the work to lift the weights higher and higher. So for each weight I add a certain potential energy. Now, if I remove one of the weights, the potential energy of the stack decreases. Where does the potential energy go? Well, in this case it went into attempting to accelerate my arm. There's some thermal energy involved, and let's not worry too much about where that one went, but the potential energy of the stack certainly decreased. Now it's even more obvious where the potential energy goes if I simply knock this thing off. It went into the kinetic energy of the falling weight. There's another way to make this happen. I don't know if I'm going to be able to do this without making a mess here, but let's see. Okay, I can simply pull the bottom weight out, and somehow miraculously we managed not to tip the column. I think it was right on the borderline. In that case, the potential energy of the stack also decreased, but the whole stack fell. Not as far, it didn't attain as much velocity, but the potential energy of the stack went into kinetic energy, just as the potential energy of the top weight went into kinetic energy. Now the potential energy changes were the same in both cases because we went from a state where we have a stack to a state where we have a lower stack with a weight sitting on the table here, or the board. It's just a board, it's not really a table. It looks like I'm denting it with this experiment, but so I'm glad it's not a table. Okay, so we see that there is definitely a change in potential energy of the stack that results in the kinetic energy of something or another, the falling stack, the falling weight, or whatever. Now let's imagine that these weights were really slippery and not perfectly flat, so that, and that the surface here was really slippery. So that what happens is, at some point, the bottom weight gets into the wrong position, and as a result of all that slipperiness, it gets squeezed out. So it gets squeezed out from under the stack and takes off with some velocity. In that case, the potential energy of the stack could conceivably get converted into the, did I say potential? Potential energy of the stack. Some of the potential energy could be converted into the kinetic energy of the weight that gets squeezed out. Potential energy decreases, kinetic energy increases by the velocity of this weight, as a result of the velocity of this weight. And that's kind of what happens in a fluid. When water flows out of a hole in the side of a container, it's being squeezed out. The column of water comes down a little bit, its altitude decreases, its potential energy decreases, the mass also decreases. And we get less potential energy, and that change in potential energy is largely manifested by the kinetic energy of the water that flows out of the container. Okay, let's move this out of the way, and let's look at how we might analyze the situation. Our model is a uniform container cross-sectional area, and we're going to do a numerical example first, a cross-sectional area of 8 square centimeters. And let's say it's 90 centimeters, and implicitly the hole is down here at the lowest point. And let's say that we have a ½ centimeter cylinder of water at the top, and we're going to ask what happens as that ½ centimeter of water flows out. Okay? Now, we want to find the change in the potential energy of the stack. The change is just the change in the potential energy of this water as it leaves here and gets replaced by water flowing out here. So it's going to be the potential energy of whatever this mass is at a height of 90 centimeters, approximately. We might want to hedge a little bit and say, well, really it's 89.75 centimeters on the average, and if you want to do that, you're absolutely right. But we're just going to do a ballpark calculation here, because eventually we're going to let the width of this thing become insignificant. Okay, so what's the mass of this? Well, how are we going to get the potential energy of this thing? Our scheme is going to be, we can find the volume. If we can find the volume, we can find the mass. It's water. We know how much water is per cubic meter. We can find the volume in cubic meters. We find the mass, which tells us what the weight is, which will then tell us what the potential energy is when we combine it with the height. We run through the calculations. The volume is just the cross-sectional area times the height of the cylinder, and the cylinder we're talking about is the red shaded cylinder, just the small cylinder of water up top. So that's going to have a volume of 8 square centimeters times its half centimeter altitude, or 4 cubic centimeters, 4 times 10 to the negative 6 cubic meters. What's the mass? It's density times volume. Density is rho. Remember what rho looks like. Okay? And we multiply that density, rho, which is 1,000 kilograms per cubic meter squared, cubed, times the volume, which is 4 times 10 to the negative 6 cubic meters, and get 4 times 10 to the negative 3rd kilograms, which is 4 grams if you wish. The weight then is what gravity does, the force exerted by gravity on that mass, which is mg, which comes out 3.92 times 10 to the negative 2nd newtons. Its potential energy is the weight times the height, which comes out to 0.0353 joules. So that's the potential energy of this bit of water at this altitude. Now, when the system changes from having the water at the top to having the water down here at the bottom, there's a change in potential energy, and that's what we just calculated, the 0.053 joules. Because the water at the top is no longer there, we lose that potential energy. So that the change in kinetic energy is minus the change in potential energy. Change in potential energy is a negative 0.053 joules. The kinetic energy change is therefore positive 0.053 joules. V naught is 0. That is, the water in the column really isn't moving very fast. The water up at the top of the column wasn't moving very fast, although it did in fact have a small velocity. So we're going to still say approximately that V naught was 0. So that the 1/2 mv squared is going to be your entire 0.053 joules. So that the velocity of this water we obtained by solving this equation with m equal to the mass that we found over here, the 4 times 10 to the negative 3rd kilograms. Somebody told me that that was 0.13 meters per second. I don't think that's correct. I think you need to plug that mass in here and actually find what this velocity ought to be. But I think it's a little greater than 1.3 meters per second.